Now for section 2.7 on quotient spaces, an idea you've encountered before, probably in algebra. In modern algebra, you study a quotient group of a given group with respect to a normal subgroup. Now, this normality stuff is no concern for us. We're going to look at quotient spaces. There's parallels with the behavior of quotient groups, not so much a parallel with these concerns about normality from the group theory setting. But given a group and a normal subgroup, G and N respectively, we'll denote G mod N is how this is read as the group of cosets of N in G. So the elements of a quotient group are sets of elements of the original group G, and they are, in a sense, they're based on that normal subgroup N. These cosets exist whether the subgroup is normal or not, but you can't make the quotient group unless you have a normal subgroup. The important observation to tie this closer to what we're doing is the fact that the cosets, that is the elements of the quotient group, are equivalence classes. They're equivalence classes based on, it's often called congruence modulo capital N, modulo that normal subgroup. But this idea that the cosets or equivalence classes is quite similar to what we're doing here when we address quotient spaces. Some more details can be found in senior level algebra notes or graduate level algebra class, and there's some links to some of my stuff for those classes given in the online notes. Okay, so we're going to define an equivalence relation as follows. Let N be a subspace of a linear space X, so entirely in our linear space realm, N being used to denote the subspace, sort of taking its inspiration from the normal subgroup stuff that you see in groups. But we'll take for X and Y vectors in normed linear space capital X, define the equivalence relation X is related to Y if X minus Y is an element of it. If the vector difference is in this subspace, then we're saying that vectors X and Y are equivalent. Equivalent mod N would still be a reasonable type verbiage to use. So denote the equivalence class under this equivalence relation, which contains element X as X bar. Very different things. This is similar to the notation used in algebra, where the bar indicates an entire equivalence class of things. It's a set of vectors for us. It's a set of group elements in quotient groups, or specific sets or cosets. But here we're getting these equivalence classes, and this is the equivalence relation. We'll make a claim this is an equivalence relation. That's fairly easy to establish. Reflexive, symmetric, and transitive. Pretty straightforward. N's a subspace. It's closed under vector sums. So it's pretty straightforward to get transitivity, and the others are virtually trivial, reflexive and symmetric. But this is an equivalence relation. You know, equivalence classes partition a set. That's one of the main reasons you look at equivalence relations. If we take vector X from the big normed linear space, capital X, let me refer to it verbally like that, N's a subspace of the big space, capital X. So for vector X in the big space, denote the equivalence class containing it as X bar, as we did before. The equivalence classes are called linear manifolds, verbiage we won't make great use of, but to illustrate that terminology, suppose the big space is R2, so we can draw pictures. And N is a one-dimensional subspace of X. That means if we take all the vectors in capital N, this subspace, and put them in standard position, they'll determine a line in R2. And we'll see that the other equivalence classes have a geometric relationship when in standard position. So with x equals R2 in a one-dimensional subspace of x, the equivalence classes on x form a collection of lines parallel to n in x. Again, with all the vectors put in standard position. Quick side comment, you ever talk about vectors lying in a plane or vectors determining a plane, vectors lying along a line, all these geometric interpretations of vectors in Rn only make sense if those vectors are in standard position. That is, with their tails at the origin and the heads wherever they may lie. So what we're getting then is this kind of situation. Here is subspace N. All right, it's a one-dimensional subspace in R2. Usual interpretation of vectors and points here. That means all the vectors in this subspace N are vectors that, when in standard position with their tail at the origin, the head will lie somewhere along this blue line. The heads of those vectors, usual geometric interpretation. When we look at the equivalence classes, we're getting these red lines. We're getting lines parallel to the blue line, parallel to the subspace in a sense. What they are, to speak geometrically about them, they're translations of N. We've taken N and to that set of vectors added, say, the vector Y, which would produce this particular equivalence class, X bar. Now, vector X is in this equivalence class. X bar means when that vector is in standard position, vector X is in standard position with its tail at the origin, the head of that vector lies along the red line. So that's the geometric interpretation. And this is the general idea of quotient spaces. We're taking a linear space and ultimately partitioning it up into equivalence classes. And the equivalence classes have, if you're sufficiently careful, especially with the standard position stuff, they have a neat little geometric interpretation. The set of all equivalence classes is denoted X mod N. We'll read that X mod N just like we would in the quotient group setting. We're going to define addition and scalar multiplication on X mod N as follows. So the elements of X mod N, soon to be called a quotient space of X and N, the elements of the quotient space are equivalence classes. Equivalence classes under the equivalence relation mentioned previously. So to define addition on this quotient space is to define what it means to take equivalence class X and add it to equivalence class Y. The output should also be an equivalence class. We'll define it to be the equivalence class containing X plus Y. You want to take an element of the quotient space and multiply it by a scalar alpha. Then you take alpha, multiply it by an equivalence class, X bar, and produce an equivalence class. We're defining that to be the equivalence class alpha X bar. In other words, the equivalence class containing the vector alpha X. So there's definitions of addition and scalar multiplication. If you're experienced with algebra, your immediate concerns become, is this well defined? And we did this in terms of representatives of equivalence classes. X bar is the collection of all vectors in normed linear space capital X, the big space, that are equivalent to vector X under the equivalence relation defined above. Well, there's a whole bunch of vectors there. How do you know if I choose different representatives of this equivalence class, and the same goes for equivalence class Y bar, that yields the same equivalence class on the right-hand side? In other words, how do you know this addition here is well defined? Because we're defining it using representatives from equivalence classes. And the same goes for the scalar multiplication. We need to check that. I'm going to leave it as exercise, an exercise I inserted, exercise 2.A from chapter 2, to go through and confirm that these definitions of vector addition and scalar multiplication are in fact well defined. That is, they're independent of the representatives chosen here. A quick little warning about that exercise. The overlines represent equivalence classes, as they do in algebra. We're dealing with scalars here as well. Those scalars could be real, those scalars could be complex. Don't confuse the overline in this setting with complex conjugate. There was no alpha bar in any of this. There was alpha, the scalar, times x bar, the equivalence class. And there's the equivalence class containing the vector alpha x. There's no conjugation implied by this. There's only so many symbols. But don't confuse in any way this overline stuff with complex conjugation. X mod n becomes then a linear space if, in fact, these operations of vector addition and scalar multiplication are well defined, and we're calling, and they are, as shown, to be shown in the exercise, and we're calling the resulting linear space the quotient space of X, or the quotient space of X and capital N. A mapping, pi sub n, we're going to call it the canonical projection with respect to capital N. Pi sub n, define this mapping from the norm linear space X to the quotient space X mod n, by taking an element, a vector, of the big norm linear space capital X and associating it with an element of the quotient space. All right. Yeah, elements of capital X are vectors. Elements of X mod n, the quotient space, are equivalence classes of vectors. So we need to map a vector to an equivalence class. We're going to do so as follows. Define pi sub n of X to be the equivalence class containing X, the equivalence class in the quotient space containing X. The equivalence classes partition up the set on which the equivalence class is defined, capital X. So there's certainly some equivalence class that contains X. So this is meaningful. So we'll define that as the mapping. Again, it's called a canonical projection. It's probably not one-to-one. Remember, the equivalence class containing X could contain a bunch of stuff. And your standard example of this kind of thing, though not from a linear space setting, would be an idea of congruence mod n, when you consider the integers mod n. There's a bunch of integers that are 0 mod n. There's 0, there's n, 2n, 3n, negative integer multiples of n. So same idea here. This equivalence class could contain a bunch of stuff. Well, all that stuff is mapped by pi sub n to the same equivalence class. So I don't expect this to be one-to-one. This same idea is addressed in quotient groups. The pi sub n there is called variously, it's called a canonical homomorphism in the senior level algebra class. There's a link to some notes relevant to that and some results about it. The fact they're calling it a homomorphism is showing that it preserves somewhat the structure of a group in some sense. It's not an isomorphism, so maybe it doesn't preserve all structure, but it preserves some of the structure of a group's. Here, we're dealing with pi sub n. The structure that we have is that of linear combinations, and we're about to claim in lemma 2.7.a that the projection, canonical projection, is a linear operator. Well, if it's linear, then it's preserving the kind of structure that we're interested in. But in the group setting and quotient groups, sometimes called a canonical homomorphism, in the graduate level class, the book I use in that class calls it the canonical epimorphism. Epimorphisms involve surjectivity So we're about to see that this term is more in sync with the terminology that we have here. But anyhow, there's some links to that as well. These are common things to consider when looking at quotient groups or quotient spaces. So lemma 2.7a, I'll leave this as an exercise as well, says the canonical projection is onto, and that shouldn't be surprising at all. You're mapping elements of equivalence classes onto the equivalence class, which contains them. So no surprise about the onto-ness. And the claim is this is a linear operator as well. So we need to establish linearity and observe the onto-ness to get a proof of that. But this projection then, similar to the group setting, it's preserving some of the structure. Our structure is linear combinations, and they're preserved by linear operators. So there's some parallels between the group setting and the norm linear space setting again. Okay, we're going to take a linear transformation from x to y and write it as a composition of a couple of special kinds of transformations at this stage. Suppose t is a linear transformation from x to y, has null space n of t, a notation we've used a little bit. I'm going to use a little bit more now. Kind of similar to what we had above. We used n to represent simply a subspace of a linear space. Here it's a subspace that's intimately related to the linear transformation t. It's the null space, everything mapped to the zero vector by transformation t. Based on transformation t and its null space, define a mapping t tilde, mapping the quotient space x mod n of t into space y as follows. Define t tilde of x bar to be t of x. Okay, let's dissect this and see if this makes sense. Does it really map an element of x mod n of t to y? We're defining it, t tilde is acting on x bar, that's an equivalence class in this quotient space. So it is taking the right kind of thing in. And it should give us out something in space y. It gives out t of x. Well, t of x is in space y because transformation t maps x to y, norm linear space x to norm linear space y. So the setting is correct. T is linear, then so is t tilde. Straightforward to establish that. T tilde is 1 to 1, whereas t may not be. T tilde is 1 to 1 is the claim, injective if you like. Since if we have t tilde of x bar equal to t tilde of y bar, if we get those equal, then we're going to draw the conclusion that x bar equals y bar. Same thing out implies same thing in, if you will, in terms of one-to-oneness. Let's go through the argument for that. T tilde of x bar, by definition, is t of x. T tilde of y bar, by definition, is t of y. So if we have equality of the t tildes, that implies equality of the corresponding t's and the corresponding representatives x and y. So we get t of x equals t of y. Well, if t of x equals t of y, by the way, notice those both live in this space, then we have t of x minus t of y equals 0. That's clear which 0 we're talking about there. It's implied by the setting, but remember, t takes us into y. This involves t of x minus t of y. So this must be the 0 vector in space capital Y. There's also a 0 vector in space capital X as well, and there's also a 0 scalar out there. We've been through this, but we can tell from the symbols what the setting is and which 0 that is. It's a 0 vector in the norm linear space capital Y. So we get t of x minus t of y must equal 0 since t of x and t of y are equal, as argued here. T is a linear transformation, so we can rewrite t of x minus t of y as t of x minus y. Hey, that means x minus y is a vector in capital X that's mapped to the 0 vector in capital Y. That means X minus Y is in the null space of T. The null space of T is the stuff that T maps to the 0 vector. It looks like this vector X minus Y is one of those things. So we get X minus Y is in the null space of T. But in terms of the equivalence relation we defined above, we define the equivalence relation. X is related to Y if and only if X minus Y is an element of N, where we started with any old subspace of space X. That's how we define the equivalence relation above. Okay, well, we've got a subspace N is determined using transformation T, but it's the same thing. We still got some subspace N of T. So we get X is equivalent to Y in terms of the equivalence relation determined by subspace N of T. Or in other words, the equivalence class containing X and the equivalence class containing Y are the same. They are equivalent. X and Y lie in the same equivalence class. Same way of saying this. It's just notation for X is related to Y. Similarly, if X is related to Y, then the equivalence classes are the same. And so T tilde of X bar equals T tilde of Y bar. So what we've shown here is we get T tilde of X bar equals T tilde of Y bar if and only if X is related to Y. That allows us to draw the conclusion that we get equality here if and only if we get equality here. The inputs are the same. T tilde of X bar equals T tilde of Y bar if and only if X bar equals Y bar. And that's what X related to Y means, is X bar equals Y bar. Very definition of one-to-oneness. So we have a one-to-one, or if you like, an injective mapping here. The projection operator, pi sub n of t, maps X into the quotient group, X mod n of t, is onto, as we claimed above, and as should be fairly straightforward. So what we can do is take t and write it as t tilde composed with n of t. T tilde will take a, remember, reading function compositions, we read the one on the right first. This will take input from X and give us output in the quotient space. And then T tilde takes, T tilde, here it is, T tilde takes the quotient space and maps it into Y. We can write T as the composition. We've got the equality determined right here. That's the very definition of T tilde, in fact. And we've taken T and written it in terms of T tilde composed with the canonical projection operator. The benefit of this being we've expressed T as the composition of a one-to-one mapping. We saw T tilde was one-to-one. And with an onto mapping. And we saw the canonical projection operator was onto, as we claimed upstairs, surjective. We're not saying T itself is one-to-one and onto. We sort of picked a one-to-one part off and an onto part off. The mapping T tilde composed with the canonical mapping sort of maps X through the quotient space and then to Y, whereas T just maps us straight from X to Y. Okay, let's introduce another norm. We'll have to show this thing as a norm. Not surprised to see norms appearing somewhere and all this stuff. We've got a new linear space, the quotient space. Is it a norm's linear space? Yeah. I'm going to define a quantity, and we'll need to go through and establish that this quantity actually does determine a norm. For X bar in the quotient space, equivalence class in the quotient space. Define the norm on the quotient space as norm of x bar is defined as the infimum of the norm of x minus z such that z is an element of subspace capital N. And in fact, this is the same way back when we were first introducing metrics. It's the same way we define the distance from a vector to a set of vectors, distance from a vector to a set in a norm linear space setting. A couple of things to unwind from this. Z is kind of like a variable. It ranges over subspace capital N, and we take an infimum of all resulting norms given here. Okay, these norms, norm of x minus z, where's that norm? That'd be the norm in linear space x itself. X is a vector in capital X, z is a vector in N, and N is a subspace of X. So X and Z are both ultimately elements of norm linear space X itself. So this norm is a norm in that space. So we're taking an infimum for a given X value over all such norms. Hey, these norms are non-negative real numbers. The infimum exists. As Z ranges over subspace capital N, now something subtle, but something that should concern you. X bar, that's an equivalence class of a whole bunch of vectors. We just picked one. We picked X itself in this definition. But this isn't well defined unless it's independent of the representative of this equivalence class. For example, like we had upstairs, if X is related to Y, that is, if X bar equals Y bar, so if Y is another element of this equivalence class, we ought to be able to replace that X with a Y and get the same thing. That is, this needs to be well defined. And it is, here's why. Suppose we choose X and Y both from the same equivalence class, X bar. What does that mean? That means X minus Y is in N. That's how the equivalence relation is defined a couple of pages back. So if we take an infimum over the norm of X minus Z, so we've chosen X to determine this quantity, and let Z vary over N. We could also write that as the infimum of the norm of X minus, parenthetic statement, Z plus X minus Y. All right. So as opposed to letting Z range over all of N, we're going to take Z and translate it by an amount X minus Y. But X minus Y is a vector in capital N. So as Z ranges over capital N, over here, we get the same set of numbers as Z ranges over capital N here. As Z ranges over capital N here, these vectors will also range over all of capital N. So we're not claiming, of course, that Z equals the quantity highlighted, but as Z ranges over capital N, we get the same set of vectors over here as we get over here. We've simply taken the Z vector and added something in capital N to it. I mean, that's why we made that observation there. So we get equality here because N is a subspace and we're really taking an infimum over the same collection of vectors. They just look a little different on the right-hand side. Since we're dealing with this representation here, next step is easier. We can simply simplify that. We've got X minus X, so we lose that. And then we're left with Y minus Z. When you simplify the arithmetic here, you're left with a Y minus Z. Z still ranges over all of N, and that's exactly what we wanted to claim. We could use representative X or representative Y from that equivalence class X bar. Doesn't matter, equals equals. You get the same thing. So our definition of the norm of equivalence class X bar, it is well defined. It's independent of the choice of representatives used from the equivalence class. Okay, final claim. We'll go through proofs of all of these parts here. We're taking N to be a closed subspace. It's the first time this word has appeared. We'll need that hypothesis in what we're doing. N's a closed subspace of a norm linear space X, I mean topologically closed in this case. The quantity, norm of X bar, really is a norm on the quotient space, so that's to be established. What is a triangle inequality, scalar property, and the only vector with norm 0 is the 0 vector. Definition of norm we had back at the beginning of the chapter. So we'll establish that. Claim is if X is a Banach space, then the quotient space is also a Banach space. The norm of the canonical projection is 1. And if N is the null space of some bounded linear operator T, then T tilde mapping the quotient space into X, defined as we did above, T tilde of X bar equals T of X. Claim here is this has the same norm as T. The norm of T tilde and the norm of T is the same. So there's the claims. Let's go through them one at a time. Okay, the lengthiest one's probably part A. Not that it's complicated. We'll have to use some epsilon arguments on this since norms are defined in terms of infima. In fact, recall, for X bar in the quotient space, we define the norm, okay, legal disclaimer, the alleged norm at this stage, but we can safely call it norm when we complete the argument. The alleged norm on the quotient space was defined as norm of X bar is the infimum norm of X minus Z as Z ranges over all N. We won't use this, but we've observed that that's a distance between a vector and a set of vectors. So the norm is defined as an infimum. Take X1 and X2 to be any vectors in X. Choose any epsilon greater than 0. We want to show that the norm of X bar plus, the norm of X1 bar plus the norm of X2 bar is less than or equal to the sum of the norms. So we're trying to show the triangle inequality here. We've chosen arbitrary vectors in X. So that'll lead to an arbitrary element of the quotient space, X1 bar and X2 bar. Arbitrary epsilon greater than 0. All right. The norm of X1 bar is an infimum of the norms of all X1 minus Z1, where Z1 ranges over subspace capital N. Definition, this norm equals the infimum over here. All right, so the norm of X1 bar is itself an infimum. What we're doing is adding a little bit, let's add epsilon over 2. We've added a little bit to that infimum. Well, infimum was, forgive me, it was like the smallest. What is it? Not exactly the smallest, some sort of limiting value involved in this, but to make some informal sense of it, this was like as small as things could be. We added a little bit to it. Okay, well, if this was the infimum and we've added a little bit to it, then there's an element of the set over which we're taking the infimum that's less than that. I can't say there's something in the set that equals the infimum, but I can say if you add a little bit to the infimum, I can find something that's close to that. It's less than the infimum plus epsilon over 2. So that's how we know there exists Z sub 1, an element of capital N, such that the norm of X sub 1 minus Z sub 1 is less than the infimum, the norm of X1 as we've defined it in terms of an infimum, plus an epsilon over 2. Properties of infimums. Maybe review some senior level analysis if you find that puzzling. Definition of infimum. We can do the same thing over here with the X2. It's an infimum, add a little bit to it, we can find a specific z2 in N such that the norm of x minus z2 is strictly less than this quantity. We bring that up because it's the norm of the equivalence class x1 bar plus the equivalence class x2 bar. It's that thing we're interested in dealing with a triangle inequality. How do you add x1 bar to x2 bar? That is x1 plus x2 bar, the equivalence class containing x1 plus x2. That's how we defined addition in the quotient space, and it's well defined as commented. All right, this is also an infimum, since it's a norm, alleged norm of an equivalence class. So if we take a specific z1 plus z2, and we're given specific z1s and z2s above, we take specific z1 plus z2. This will be an element of N, right? Right, N's a subspace, so it's closed under vector sums. So let's take this as the element of N, a specific element of N. We take the norm of x1 plus x2 minus this element of capital N. That's a specific element of the form vector minus element of N, x minus z, norm of is how we dealt with it previously. Well, it's a little more complicated because the vector we're interested in is x1 plus x2 here. So we take the x1 plus x2 here and subtract a specific element of capital N. But this is defined as an infimum. So if we take a specific one, that's going to give us something greater than or equal to this infimum. That's a little more straightforward. Up here, we introduced the epsilon and wiggled around the infimum in a sense. But here, hey, that's an infimum. This is a specific element of the set over which we take that infimum, so greater than or equal to. Now, we did that so we could take the argument from an argument about these alleged norms on equivalence classes to straight up norms of vectors. This norm here, which norm is it? That'd be the norm on capital X, the big norm linear space. How can you tell? Because x1 and x2 are from capital X, and so are z1 and z2. So this is a vector in capital X. Hey, in capital X, that's a norm linear space, so the norm there satisfies a triangle inequality. We've got the norm of ultimately a sum of two vectors. So split it up in the appropriate way using the triangle inequality in the big norm linear space, capital X. All right, so it's a matter of shifting the question from the new setting, the quotient space, to the old setting, norm linear space, capital X, and back, standard math technique. How big is the norm of x1 minus z1? Well, we chose it to be less than the norm of x1 bar plus epsilon over 2. Similarly, x2 minus z2 in norm, if we chose the z2 such that that's less than x2 bar plus epsilon over 2. So simply replace this and this with these two bounds, strictly less than norm of x1 bar plus norm of x2 bar plus epsilon over 2 plus epsilon over 2 will combine into a single epsilon. And we've got the norm of the sum here is less than the sum of the norms here plus a little epsilon, but epsilon greater than 0 is an arbitrary number. So that establishes by saying this can be arbitrarily small, can't be 0, and preserve the strict inequality, but we know this quantity must be greater than or equal to that quantity, and that's standard use of epsilons in an epsilon argument. In a sense, we're taking a limit as epsilon approaches 0. And then that changes strict inequalities into non-strict inequalities, and we do get exactly the triangle inequality out of that. So the norm we've defined satisfies a triangle inequality on the quotient space. We need to check the scalar property. Let's do that one next. So next comment is, take an arbitrary vector from normed linear space X and a scalar, a non-zero scalar. Of course, the scalar field will be the reals or the complex numbers. We could do this over any scalar field for which an idea of absolute value exists, but we'll use reals and complexes. And we can't talk this scalar property without the absolute value concept. So take alpha, non-zero scalar in the scalar field, let it be fixed. And for any z in n, we have alpha x minus z in norm. Okay, this is the norm on normed linear space X, and we know it behaves properly. In particular, we can factor the alpha scalar out using the scalar property on the norm on normed linear space capital X. Take the alpha, stick it back in, it reduces to this. We're getting a z divided by alpha, well, 1 over alpha times vector z here, and that's the reason we needed the non-zero observation there. X minus z divided by alpha, this is of the form x minus an element of capital N. Z was in capital N, so z over alpha is in capital N. Well, if we have a specific x minus element of capital N, you know that's greater than or equal to the norm of the equivalence class containing X, because that norm is defined as an infimum of these kinds of things, X minus element of N. It's actually fairly simple, fairly similar to the arguments we've made right here. But we get a greater than or equal to because this is an infimum over a set of values, and this is one of those values. So the inf is less than or equal to a particular value in a given set. So let's see, we've established an inequality here. If we take an infimum over all z, then preserving this part here, infimum over all z, infimum over all z here, we've taken a vector minus an element of n. That vector is alpha x. Take an infimum of this quantity as z ranges over all n's. That will produce the norm, alleged norm, on the equivalence class containing this vector. That produces the norm on alpha x bar, the equivalence class containing alpha x. Taking an infimum over all z on this side, you've got this greater than or equal to this. Strictly speaking, this is a constant. Alpha, absolute value of, is a constant. The norm of x bar is some constant. We take an infimum on this side. If all the terms are greater than or equal to this constant, then the infimum of this is greater than or equal to that constant as well. In other words, the norm of the equivalence class containing alpha x is greater than or equal to, I think a little hidden by the dark part at the bottom of the screen, but greater than or equal to absolute value of alpha times the norm of x bar, this constant over here. By the way, that if alpha equals 0, that holds as well. For some algebraic reasons, we couldn't use 0 in this computation. This is the conclusion. Yeah, that conclusion holds even when alpha is 0, by the way. Okay, so we've got the norm of the equivalence class alpha x, equivalence class alpha x bar, is greater than or equal to absolute value of alpha times the norm of x bar. We need to reverse that inequality and draw the conclusion of equality. That's the scalar property. So we're halfway through the scalar property. Next. Again, it's going to be a little bit of an epsilon type argument. Given r greater than 1, choose z sub 0 in subspace n such that x minus z sub 0 is less than r times the norm of x. Okay. Norm of x is defined as an infimum. We've got something a little bit bigger than the norm of x. R is greater than 1, so r times the norm of x is greater than, actually strictly greater than norm of x. R is strictly greater than 1. So I could change this to a strict inequality. So on the right-hand side, we got something a little bit bigger than the infimum. Well, that means there's an element of the set that's less than that, less than or equal to that. if you like. That is, there's a z sub 0 in capital N such that this norm is less than or equal to this thing, which is a bit bigger than the infimum. Properties of infimum. So with that choice of z sub 0, then if we look at alpha x equivalence class, norm of, that's less than or equal to alpha x minus alpha z sub 0, because how would you define this norm on the quotient space? By taking the representative alpha x and subtracting an element of n. We're choosing the element alpha z bar. This is an infimum, as we've defined it. This is a particular element of the set over which we would take the infimum. It's vector minus element of n. So this particular element of the set is greater than or equal to the infimum of the set. Definition of infimum. The benefit here is now we've got an expression involving norms in normed linear space capital X. It's kind of similar to the stuff above. In capital X, we can use the scalar property on the norm on capital X. So we can bring the alpha out front in absolute value. That leaves us with an x minus z sub 0 in norm. But we've chosen z sub 0 such that the norm of x minus z sub 0 is less than or equal to r times the norm of x bar. Use that inequality here to introduce this. That's stated. That's how we chose the z sub 0. Now we've got alpha x bar, norm of, less than or equal to absolute value of alpha times parameter r times the norm of x bar. We need to get rid of the r. Well, this holds for all r greater than 1. So it also holds for r equals 1. Take a limit of both sides. Take a limit as r approaches 1 from the positive side. This is a constant. And the r here will have a limiting value of 1. It's a common trick with inequalities to deal with limits like that. Leading us to the conclusion that alpha bar norm of is less than or equal to the absolute value of alpha times the norm of x bar. That's the reversal of the inequality we had on the previous slide. And so we can draw a conclusion of equality, and there's the scalar property. So we got the triangle inequality for this alleged norm. We've got the scalar property for this alleged norm. The last thing to check is norm equals 0 if and only if x bar equals 0. So that's what we're establishing. With that established, then this thing satisfies all three properties of the definition of a norm, and so is a norm. Okay, x bar, norm of, equals 0 if and only if, this is the definition of x bar, norm of, the infimum of x minus z, norm of, as z ranges over, subgroup capital N, if that thing equals 0, because that thing is the norm of x bar. Well, this holds if and only if. The only way we can get this infimum to be 0 is if this vector is the 0 vector. That is, if x is a vector in N. If x is in N, then this norm will equal 0, actually take on the infimum value. And that's supported by the fact that N is a closed subspace. So the only time we can have distance, have an infimum of 0 when we're dealing with a closed set is when that infimum actually is attained as a minimum, because we're dealing with a closed subspace. So that's why we needed that little hypothesis added in. That allows us to draw the conclusion that we must have x in N itself. And then when we take an element of N, we subtract z as z ranges over all elements of N. That norm can equal 0 simply when z equals x. So the infimum then is 0, and that requires x to be in capital N. Again, since we're dealing with a closed space, topologically closed. Since N is the additive identity in X, the quotient space, x mod n, similar to the behavior in terms of quotient groups. Then, since x is an n is the additive identity, and look at the way we add equivalence classes together, then we've got x bar norm of equals to 0 if and only if x bar equals n, and n itself is an equivalence class. That should be clear. Maybe look back at the definition of equivalence relation. But we get x bar equals n, and n is the 0 vector in this quotient space. So what we've shown is norm of x bar equals 0 if and only if x bar is a 0 vector. It's the 0 vector in the quotient space. So which 0 is this? It's the equivalence class containing the 0 vector, which turns out to be capital N itself. So third property is satisfied, and this thing that we've defined satisfies the definition of a norm on the quotient space. So no longer is it simply an alleged norm, it's a norm. So we've got a norm on the quotient space, and it's defined in terms of these infima. Next claim, if x is a Banach space, then x mod n is a Banach space. The quotient space here is a Banach space. Okay, we're going to address this in terms of absolutely convergent series. And we're going to use Theorem 2.12. Let's run and take a look at Theorem 2.12. I think I got it hidden in the background somewhere. Here we go. Theorem 2.12 says a normed linear space X is complete if and only if every absolutely convergent series is also convergent. We're talking Banach spaces. Banach spaces are complete normed linear spaces. So we can address completeness by addressing this property. Absolutely convergent implies convergent. So that's the plan here. So let's take a series in the quotient space, sum I equals 1 to infinity of x sub I bar. Suppose this is an absolutely convergent series in the quotient space. If we can show it's also convergent, then we've shown that space, the quotient space, is complete. That is a Banach space. We do already know that x mod n is a linear space, a normed linear space by part A. For each I, a natural number, choose z sub I in the subspace capital N, such that the norm of x sub I minus z sub I is less than or equal to the norm of x sub I bar plus this 1/2 to the I. Think of that as epsilon. Same thing that we did previously. We've gone a little bit bigger than the infimum. If you go a little bit bigger than the infimum, you're picking up elements of the set over which you're taking that infimum. And we're taking the infimum over vectors x sub I in this case, minus elements of subspace capital N. So choose the z sub I satisfying this inequality can be done because this thing is defined as an infimum, properties of infima. Do that for all natural numbers. So then when we look at the sum from I equals 1 to infinity of the norm of x sub I minus z sub I, we've got something less than or equal to term by term replacements on these inequalities. This quantity is less than or equal to this quantity. So we'll just simply replace term by term. You get something that's greater than or equal to. And by the way, we've got convergence here. We assumed the x sub I bars are absolutely convergent. What does that mean? That means the sum of the norm of those terms is finite. So the hypothesis of absolute convergence here gives us that this part is finite. What's up with the sum of the rest of it? These are powers of a half. We're summing from 1 to infinity. The sum is 1. geometric series. Oh, and we can write the series as individual sums. We can use the rearrangement theorem because both of these constituent parts are convergent. Geometric series, it converges to 1 here. This thing converges. These are just series of real numbers, right? The norms are real numbers. And we get that absolutely convergent by hypothesis. This is finite by the absolute convergent hypothesis. This is a 1 because I know some things about geometric series. So anyhow, what we've got is finite here. So we've shown that this thing here, this series of real numbers, is finite. In other words, since these involve norms of x sub I minus z sub I, a bunch of vectors, then the corresponding series of vectors is absolutely convergent. So the series of x sub I minus z sub I of vectors, that's absolutely convergent because when we take the norms of all those vectors and sum them, we get something finite, as we just established. Absolute convergence of this. X is a Banach space. X sub I minus z sub I, these are vectors in X. Vectors in X that form an absolutely convergent series. Hey, in a Banach space, absolutely convergent series converge. Theorem 212 that we just looked at. So knowing that X is a Banach space and having demonstrated that this is absolutely convergent implies that that series is also convergent. Okay. This technique was the same thing we did before. We'd take a question and move it from one setting, the quotient space, to a different setting, norm linear space X itself. Before, it was a bunch of stuff with norms. Here, it's really a question of completeness. But, we've done the same thing. We've taken this idea of addressing completeness in the quotient space and converted it into a conversation about completeness in space X. So this is structurally similar to what we've been doing. So X is a Banach space. When we're using the hypothesis, we better be using the hypothesis. It's used explicitly right there to get the convergence of this series. Remember, what we're still trying to show is this absolutely convergent series in the quotient space is also convergent, and that'll establish completeness of the quotient space. Here we're using the completeness of space X. It's a Banach space. Pi sub n. It's linear. It's going to be shown to be bounded below. So we're doing this a little bit out of order, but we'll show boundedness of the projection operator here shortly. Hey, bounded operators, bounded linear operators are continuous. Theorem 2.6, boundedness is equivalent to continuous in terms of linear operators. So since we know we've got boundedness and linear, then we know we've got a continuous operator. So if we take pi sub n of x sub I minus z sub I, that was the equivalence class containing this vector x sub I minus z sub I. But the equivalence relation involved differences being in capital N. So we can actually drop the element of capital N from that, and we get that this projects onto the equivalence class containing x sub I, and that's also the equivalence class containing x sub I minus z sub I. Those are two different representatives of the same equivalence class. So I can certainly say this. So if we look at pi sub n times a series, 1 to infinity, x sub I minus z sub I, all right. We observed pi sub n is continuous. This series, and what's a series but a limit of partial sums. So this infinite series here is actually a limit of a sequence of partial sums. Can you bring that limit outside of the pi sub n? Yeah, you can bring limits outside continuous things, and we got a continuous thing, continuous function. It's a projection operator. But anyhow, the continuity lets us bring the limit outside. In other words, I can take the pi sub n inside the limit. Then we're dealing with partial sums. In particular, we're dealing with finite sums. Pi sub n applied to a finite sum is the sum of the pi sub n's. So that's where you're using the linearity. So you might want to think through this slowly. Continuity lets us take the limit outside, and we didn't explicitly write the limit out, but it's there because this is a series. Series are limits of sequences of partial sums, and partial sums are finite. But we can bring the limit outside, and the pi sub n is reaching a collection of partial sums. Partial sums are finite. The linearity lets us take the pi sub n inside the summation. Then we reach a pi sub n of x sub I minus z sub I, but we just observe that that equals x sub I bar. So we get the x sub I bars here. And the sum of the x sub I bars is convergent. In fact, it converges to this thing here. We know the sum of x sub I minus z sub I, that series, we know that's convergent to some element of space capital X. And this is simply the projection of that element onto its equivalence class. That's what this converges to. It says right there they're equal. So this series converges. We've taken an arbitrary series that's absolutely convergent and shown that it is convergent. That's sufficient by Theorem 212 to show completeness. So the space that contains this series, the quotient space, it's complete. We know from above it's a normed linear space. That is, the quotient space is a complete normed linear space. It's a Banach space. So X mod n, the quotient space, is a Banach space. Again, it's pretty similar arguments. This one had a few more details. There's a fair amount going on in this little equality right here. This equal sign contains continuity and some interactions with limits, standard analysis stuff, but there are a lot of moving parts going on with that single equality. Next, the claim is the operator norm of the canonical projection is 1. Okay, let's just go through that. I think this isn't too long. The operator norm is defined, is given here. Operator norm, remember, was a supremum, not to be confused with this quotient space norm thing that we're dealing with recently. Operator norms were defined as soups of norms when the operator is applied to all vectors x, which are unit vectors. You let x range through the space as a unit vector, and the operator norm was defined as that. Recall. Pi sub n of x is x bar, the equivalence class containing x. It projects that element onto the equivalence class containing it. That's why it's called a projection operator. And the norm of x bar is, by definition, this is what we have been dealing with recently. It's this infimum, letting the vector z range over subspace capital N. N's a linear subspace, so it contains a zero vector in particular. So one of the things we can let this be is a zero vector, in which case we get out the norm of x itself. You're taking an infimum over a whole set of real numbers, non-negative real numbers since they're norms, and one of the elements is norm of x. So the infimum, whatever it is, represented by this, must be less than or equal to that particular element. So the norm of x bar is less than or equal to norm of x. With x as a unit vector, then we'd have the norm of pi sub n of x, which is defined to be x bar, definition of canonical projection. If x is a unit vector, we know the norm of x bar is less than or equal to the norm of x. So we'll get a less than or equal to 1 under the conditions of considering x to be a unit vector. So whenever we look at this kind of thing where x is a unit vector, This thing, pi sub n of x, is bounded by 1. So when we take a soup, the soup's also bounded by 1. So the operator norm of the canonical projection operator is less than or equal to 1. I guess we want to reverse that inequality. Okay. Oops, some technical difficulties. There we go. So to an attempt to reverse this inequality, let x bar be in the quotient space and let it have norm 1, given r greater than or equal to 1, choose z, an element of n, such that the norm of x minus z is less than or equal to r. All right, it's the same thing we've been doing. It's an epsilon argument. We've hypothesized x bar has a norm of 1, norm on those equivalence classes. If this has a norm of 1, we've picked something a little bit bigger than 1. Remember, this norm is defined in terms of an infimum. So what we've done by taking an r greater than 1 is we've chosen a value here that's bigger than the norm of x. You go bigger than the norm of, x bar, bigger than the norm of x bar, there's going to be elements in that set because the norm of x bar is defined in terms of an infimum. It's, quote unquote, it's the smallest. It's more complicated than that. It's the infimum. But if we pick something a little bit bigger than that smallest value, if I may abuse the notation just to give you something tangible, you're going to get elements of the set. So we picked something bigger than the infimum more appropriately. And so we're getting elements of this set less than or equal to that quantity. Properties of infimum. Then we know, let's see, under this setting that 1 is the norm of x bar. We chose x bar to have a norm of 1. X bar is pi sub n of x minus z. Similar observation we had before. The equivalence class containing x also contains x minus z if z is in subgroup capital N because of the way we define the equivalence relation. So that's correct. I don't just get an x there. We can also get an x minus z. Same equivalence class as x. Note 2.4.a tells you when we have a bounded linear operator applied to a vector, we get something less than or equal to the norm of the vector. It's the norm of the vector times the norm of the operator. So we can replace this with the operator norm, replace this with the norm of that vector. We had chosen norm of x minus z to be less than or equal to r, so use that information here, and we get 1 is less than or equal to operator norm of the canonical projection times r. R greater than 1 was arbitrary, so we'll do that little limit trick again. Let r approach 1 from the positive side. Then we've got 1 less than or equal to norm of pi sub n. We had pi sub n less than or equal to, and norm less than or equal to 1. And so that's how we draw the conclusion of equality. Norm of the canonical operator is 1, as claimed. And now for the last part of this, we're taking N to be the null space of a bounded linear transformation T, mapping X to Y. We're taking the map T tilde to map the quotient space into Y, defined as T tilde of X bar equals T of X. This we've dealt with previously. We discussed this before. The claim here is that T tilde and T have the same norm. The norm of T tilde equals the norm of T. There's going to be a bunch of discussions about norms in this stuff. We've got a norm on space X. We've got a norm on space Y. We've got an operator norm on T. We've got an operator norm on T tilde. We've got a norm, in fact, we showed this above, on the quotient space. So that's there's like 5 different norms. So it'll be clear from the context which one we're talking about. Fingers crossed it'll be clear. So we'll try to keep track with all these symbols with norms in them, where the elements are and which norm we're talking about. Okay, proof of part C, we had shown if X as a vector in the big space capital X is a unit vector, then the equivalence class containing X in the norm that we've defined and confirmed actually is a norm. The norm for the equivalence class containing X is less than or equal to 1. So we had norm of X bar was less than or equal to norm of X, as we just saw. So if we take a unit vector X, then the norm of the equivalence class containing X is less than or equal to 1. So if we consider the norm of Tx, okay, where's this? That'd be the norm on space Y, right? Tx lives in space Y. That equals the norm of T tilde X bar. T tilde X bar and T of X are the same. By the way, being the same, it better be the same norm, the norm on Y. It is. T tilde maps us into Y. So these are both elements of Y. This is a bounded linear operator applied to a vector. So we get less than or equal to the norm of the operator times the norm of the vector. Note 2.4.a, we've used repeatedly, told us that. And X bar norm of is less than or equal to 1. So we'll replace this with 1 and pick up an inequality. And we've got, for all X a unit vector, the norm of T of X is less than or equal to the norm of T tilde. If we take a supremum over all such X, a unit vector, then the sup on this side produces the norm of T. Take a sup on this side, this is just a number, it's a constant. We've got this upper bound on all of these things where T is a unit vector. Take a sup over all such unit vectors. The sup is the norm of T and maintains this upper bound. In other words, the norm of T is less than or equal to the norm of T tilde. And that's half of it right there. Next, given X bar in the quotient space, X mod n, with norm 1, for any R greater than 1, there's a Z in subspace capital N, such that the norm of X minus Z is less than or equal to R, right? We had defined the norm of X bar in terms of an infimum. Here we've picked something a little bit bigger than the infimum, and so we get particular elements of this set less than or equal to that something bigger than the infimum, that R value. Again, same trick over and over, heavily based on properties of infimums. Then if we look at T tilde of X bar, we've chosen this X bar to have norm 1. That's the same as T of X, so we started up here. That's the same as the norm of T of X minus Z. That'd be what? T of X minus T of Z? What's T of Z? Z lives in N. N was a null space of T. So if you express this in terms of the linearity, T of X minus T of Z is T of X minus 0. T of Z is 0 because Z is in the null space of capital T. So that's the first place we've used that, I think. So this simplifies down simply to the previous. I want to maintain this form of it. Let's use note 2.4.a, this guy again. That's less than or equal to the norm of T times the norm of the vector, X minus Z in this case. We wanted to leave it like that because we had X minus Z chosen such that that in norm was less than or equal to R. So we get, I guess I need an inequality there. We get this is less than or equal to norm of T times norm of R. We'll take limit as R approaches 1 from the positive side, right? R was greater than 1, so we'll approach 1 from the positive side. This we have as a lower bound, less than or equal to this. We can draw the conclusion that we'll have this quantity bounded above by the norm of T. Then we'll take a supremum over all such X bar, changing this into the norm of T tilde. We get the norm of T tilde less than or equal to the norm of T combined with the observation norm of t is less than or equal to the norm of t tilde, and there's the equality between those two norms. And even though it just had one theorem, it's a bit of a lengthy section, that takes care of this stuff with the quotient spaces. So I will see you again shortly in section 2.8, and we're working our way towards more intense knowledge about Banach spaces is the ultimate goal here, and side order Hilbert spaces. I'll see you in the next section. Have a nice day.